Today, we're going deep underground to see how some incredible new tech, we're talking robot dogs, is keeping our subways from falling apart. Let's dive right in.
So, think about this. Right now, beneath our feet, the Earth itself is in constant motion, putting this immense, invisible pressure on the tunnels we ride through every single day. It's this slow, silent squeeze that could lead to an absolute disaster if we don't keep a very, very close eye on it.
So that begs the question, right? In these huge, dark, sprawling tunnels, how on earth do you find a tiny little warp, a deformation, before it becomes a catastrophe? Well, the answer, it turns out, involves robot dogs, lasers, and some seriously clever AI. Okay, so first up, let's really get into why this underground pressure is such a massive deal. The structural integrity of these tunnels isn't just an engineering problem. It is absolutely crucial for the safety of millions of people.
You know, even the tiniest bit of warping can have these huge knock-on effects. Structurally, you're looking at cracks, leaks, even falling chunks of concrete. Operationally, it can mess with the tracks themselves, and all of this, of course, adds up to a much higher risk of train derailments and accidents. That's why inspections aren't just a good idea, they are completely non-negotiable.
Now, think about the old way of doing this. It was slow, it was manual, relying on people taking measurements here and there. It was basically just spot checking. But the new way? It's a total paradigm shift. It's fast, it's automated, and it's all driven by robots, capturing a complete 3D picture of the entire tunnel. We've gone from a few scattered data points to a massive, incredibly detailed digital model.
All right, so let's meet the hardware that's making all of this possible. It's time to meet our new inspector.
What we're looking at is a four-legged robot. Yep, a robot dog, and it's got a super powerful laser scanner strapped to it. And its ability to walk around is the real game changer here. Unlike the old trolley systems that had to stick to the tracks, this little guy can go anywhere, navigate around obstacles, and check out all those hard-to-reach places.
And when you look at the stats, the advantages are just staggering. The cost difference alone is huge. This new robotic system is around $110,000, which is just a fraction of the cost of the old trolley systems. Plus, it's way more mobile and captures much higher quality data. So long story short, it's cheaper, it's better, and it's way more flexible.
And to really give you a sense of the power we're talking about here, that laser scanner, it's capturing 2 million data points every single second. It's literally building a digital replica of the tunnel in mind-blowing detail. And it's doing it incredibly fast.
But here's the thing, collecting all that data, that's really just step one. What you end up with is this gigantic digital puzzle, made of over 500 million tiny little pieces.
All those millions of data points form what's called a point cloud. And the best way to think about it is like a 3D model made of digital confetti. Each tiny piece of confetti is a super precise measurement. And when you put them all together, they create a perfect digital copy of the tunnel. This is what engineers call a digital twin.
In just one project, the one in the Shanghai Metro, the robot collected a point cloud of, get this, over 574 million points. Just let that number sink in for a second. That is a truly massive amount of information, capturing every last detail of that tunnel.
But here's the catch. The scanner is so good, it captures everything. Not just the tunnel walls, but every single cable, pipe, track, you name it. So the raw data you get back is actually a pretty chaotic jumble. And to find those tiny deformations in the tunnel wall, you first have to get rid of all that other junk.
And this is where the software gets really, really smart. You can't have a person sit there and sift through 500 million data points, right? It's just impossible. So you need an AI that can actually learn to see what a tunnel looks like. So our researchers built this AI model called MTPointNet. And they basically taught it to recognize and label 8 different parts of a tunnel, including the lining, that's the actual structural wall we need to analyze, and things like the catenary, which is the overhead power line. The AI's job is to go through and color code every single one of those 500 million points based on what it is.
Okay, so take a look. This is the before picture. This is what the raw data looks like. It's just this chaotic jumble of points. I mean, you can kind of make out the shape of the tunnel, but finding the actual surface of the wall with all this noise, forget about it.
And then, boom, the AI does its thing. It digitally strips away everything that isn't the tunnel lining, and what you're left with is this beautiful, clean, isolated model of the structure. This is the data you need to do a real analysis.
And this isn't just some cool trick, it is incredibly accurate. Look at the numbers. Compared to previous AI models, MTPointNet is a significant leap forward, with an accuracy score of almost 87%. That means it's much, much better at correctly identifying the tunnel wall, and, of course, higher accuracy means safer tunnels.
Okay, so we've got our clean, perfect model of the tunnel. Now what? How do we actually turn all these points into, actionable information about potential problems?
Well, it's a pretty clever four-step process. First, as we saw, the AI isolates the lining. Next, the software mathematically finds the tunnel's true center line. Then, and this is cool, it digitally slices that 3D model into thousands of 2D cross-sections, kind of like slicing a loaf of bread. And finally, it fits a perfect ellipse to each one of those slices to measure exactly how much it's been squeezed out of shape.
And the best part? The final result for the engineers isn't some complicated spreadsheet full of numbers. It's a simple, color-coded 3D map. It's basically a heat map. They can just look at it, and green means everything's fine, while yellow, orange, and red instantly point them to exactly where the tunnel is deforming and under the most stress.
So when you step back and look at the big picture, what does this all mean for the future? Well, this combination of robotics, lasers, and AI is fundamentally changing how we maintain our most critical infrastructure.
And the accuracy here is just phenomenal. When they compared this system to the absolute gold standard manual measurements, the average error was just 0.60 millimeters. That is an astonishing level of precision. We're talking less than the thickness of a credit card, and it's achieved in a fraction of the time and at a fraction of the cost.
And this really leaves us with a fascinating final thought. This technology creates a digital twin, a living, breathing digital copy of our subway tunnels. So if we can do this for tunnels, what's next? What about our bridges, our power grids, our water mains? What other critical, hidden structures can we build digital twins for and protect before it's too late?